Hi everybody. I hope you are all doing great. Welcome to this fish. Today we are delighted to have Jon Gluyas from Durham University. So Jon got his PhD in 1981 from the University of Liverpool and started his career in industry. And 28 years later, he moved to become the first professor of geoenergy, carbon capture and storage at Durham University in the UK. So his research interests, both in industry and academia, involve fluid movement in the subsurface and fluid rock interactions. Today, we will talk about decarbonization of the petroleum industry, exploring geothermal, CCS, and CO2 waste products. So please, Jon, the screen bandwidth is yours.
Thank you very much indeed. Thank you for the introduction, Adrian. I'll just find my, here we go. I momentarily lost the screen then. Well, I'm delighted to be able to talk to you today, and I hope it stimulates a little bit of interest. As Adrian said, I spent 2/3 of my career getting carbon out of the ground, and the last third trying to put it back into the ground. And my interests do span a number of things, but the common linkage is, as he said, and that's fluid movement within the subsurface and fluid rock interaction. And what I'll do today is just to give you an overview of some of the work which is going on to try and decarbonize what of course is one of the major global industries. And I'll start in what might be seen as a little bit of a peculiar place. And I can get it moving. So in the past century or so, we've seen a dramatic change, not only in global population, but the level of poverty within the global population. This is from the book Factfulness, showing that over the past, particularly the past few decades, the proportion of the growing population, which is in abject poverty, has dropped from being something like 90% or more of the global population to around about 20% or thereabouts now. And I would contend that a lot of that, and it's taken a long time to happen, but a lot of that is associated with easy access to high quality energy. And much of that high quality energy, unsurprisingly, comes from fossil fuels. You know, it's a lot easier to take your goods to market in a small truck powered by an internal combustion engine than it is with a cart, a bag of carrots, and the most willing of donkeys. Indeed, of course, we tend to measure our, particularly motors, in terms of their horsepower. And a recent purchase by myself of a new and rather posh lawnmower suggests that nominally it has 22 stallions pulling it along. Clearly, the sort of thing that you wouldn't really get the opportunity to do if we're still in a largely agrarian society. But that energy density plays out in a number of other ways. And I'll show you a couple of slides I put together a couple of years ago, thinking about this dense energy when it comes to the UK. And the UK was the first nation, it doesn't need that on, was the first nation really to start to exploit fossil fuels in any substantial quantity. It invented the Industrial Revolution, which swept around the world. And, you know, there's a weird thing here. I'm sure the anthropologists would have a field day and tell me this is complete rubbish, but you can plot the development of the British Empire, for good or bad, almost as a function of the amount of coal or the quantity of coal that was mined on an annual basis. Indeed, the peak of the UK as a global nation was in the very early years of the 20th century. And 1911 was also the peak year for producing coal. Now, the competitiveness of the UK coal dropped away, and then political expediencies kicked in by the 1980s or so, and now we produce almost zero coal. But, you know, as a nation, we got rather lucky, because as we're coming off the coal high and all that surplus energy, we managed to find North Sea oil and gas. Now, on this particular graph, I love to show it, because myself and my two sons spent a whole weekend whilst away on a Centre Parks holiday a few years ago, trying to get the flags into this Excel spreadsheet, which you see we did eventually manage. The key thing here is that the nations which you see represented by these flags have held prominent roles within the 20th century. And again, I would suggest that, added on to the political might of various nations, they are underpinned by relatively easy access to very dense, very energy dense fuels. And the UK even made it in a few years either side of the turn of the century, from the 20th to the 21st, into the top 10 petroleum, oil plus gas producers globally. But of course, it's no surprise to anyone on the planet any longer, certainly not many people on the planet, that there is now an appreciated downside to producing that fuel, or using that fuel, and in particularly combusting it. Because, of course, as you combust hydrocarbons, one of the main products is carbon dioxide, a well-recognized greenhouse gas. And you can see the growth in emissions which has occurred just over the last century or so. The USA was for a long time number one. In the last half decade or so, that's been overtaken by China. And again, this slide is from 2015 or so. In 2015, we passed the unenviable mark of 400 parts per million of carbon dioxide in the atmosphere, heading towards a 50% increase on what is calculated to be the concentration in the pre-industrial world. Unfortunately, in many ways, though, people talk about peak oil and peak hydrocarbons and so on, but we're not in the position whereby we're getting very close to exhausting resources. Admittedly, light oil is getting more difficult to find, but heavy oil and gas, and particularly coal, there is still a huge amount yet which could be won. Plenty enough to continue to rise that CO2 well beyond the scary levels which it lies at the moment. Now, in the past 10 years or so since I've arrived in Durham University, whether it be on TV or in conversation, many a folk have said, well, why don't we start to use all this CO2? And I'll come back to some possible uses later on. And even most recently, during the 2018 Football World or Soccer World Cup, hitting the television news from day to day was the fact that the UK had run out of CO2 and thus beer. And of course, that's food grade CO2, and certainly not that which is going into the atmosphere. And again, from time to time, you will see lovely little news stories on why not make all the CO2 back into petrol. And of course, the real answer lies in the graph you see on the right, that CO2 is chemically very stable. And for most things that we might want as humans, we'd need to put energy back into the system to make it into liquid hydrocarbons, for example. And the question then is, where does that energy come from, if not from burning more fossil fuel? It does have some uses. You know, if you have decaffeinated coffee, or you take your clothes for dry cleaning, then dense phase CO2 is certainly used, although how much then escapes to the atmosphere is still open to question. we can use it for stabilizing industrial waste, or in some instances, natural systems such as the CO2 injection, which is going on in Iceland at the moment, where CO2 under pressure and temperature will react with calcium and magnesium in the rock to give, well, that's what the Earth does. It produces limestone if we have a hike in CO2 in the atmosphere, but not over the sort of time period which is useful for humans. How might we tackle all of that CO2 going into the atmosphere? This particular chart was put together a little over 10 years ago now by Sokola and Pakala. They looked at the way in which emissions were rising and started to think about how you might start to ameliorate those by what they called wedges. Each of these wedges has a particular set of technologies associated with it. Carbon capture and storage, stopping deforestation, moving vehicles over to electric power, and so on and so forth. And those are the sorts of things which were suggested could let you get to a flat path. But as you'll see on that graph, which is now in the thumbnail, this was suggested in 2006 or so. And the circumstances now are that there are 8 wedges rather than 7 wedges that we would need to contemplate. Now, we will start to talk about carbon capture and storage, and you'll see at the number 7 on that list, back in 2006, was installed carbon capture and storage at around about 1,000 large coal-fired power plants. At the time when this was put together, in the following decade or so, coal-fired power stations were being commissioned at between 1 and 2 a week in China. Although they do have some CCS, it certainly wasn't on all systems. So thinking about the petroleum industry, and the central question I raised in the beginning of this talk was, how might we decarbonize the petroleum industry itself? It sort of sounds impossible in the sense that this is the prime source of energy for the whole globe, and yet we're talking about perhaps not using it or trying to ameliorate the impact in terms of emissions. And these days we can think of emissions in terms of what are called scopes 1, 2, and 3. So scope 1 is all direct emissions from operations of the activity, and that's under the control, for example, of the petroleum companies. Scope 2 is indirect emissions caused by electricity purchased and used by an organization, essentially because the power station is using fossil fuels. And scope 3 covers everything else, including products. I think, first of all, I'd like to look at scope 3 emissions. We can take from either combusted coal or gas the CO2 which is produced and remove that into geological storage. Similarly, as the new world dashes towards hydrogen generation, until such time as we can produce either natural hydrogen or sufficient hydrogen from breakdown of water using electricity, it's likely to be produced by reacting methane with water to produce both hydrogen and carbon dioxide. Again, the carbon dioxide can go to geological storage. And in terms of other industries, particularly things like steel and cement, both of which are intense in terms of their CO2 production, this time not because they're necessarily using fossil fuels, but because of the role played by limestone in creating those products. Again, we can take the CO2 to geological storage. Now, there are a number of types of storage we can address. one of the most favored is to take the CO2 captured either following combustion or using pre-combustion methods or even oxy-fuel, and put that CO2 back in the ground into depleted oil and gas fields. And that's proven. We already do that in the USA, Canada, China, Algeria, the Netherlands, and there have been, well, there's now in Australia as well, I should say, and there also have been a number of test sites elsewhere in the world. CO2 has some very useful properties while still as a gas, insofar as if you inject CO2 into an oil system, it will lead to expansion of the oil. It's a bit like keg beer. And that's been used extensively, particularly in West Texas, for enhanced oil recovery. Now, you can engineer this to be around about carbon neutral. The problem we have in the USA is not so much that CO2 is used for enhanced oil recovery, but what CO2 is used for enhanced oil recovery. When first developed in the 1970s, it was anthropogenic CO2, pioneered by Shell, as it happens. But much of it now is actually natural CO2 that need never have come out of the ground in the first place. So although the CO2 almost all is retained within the ground, this particular application is nowhere approaching net carbon zero. The other place we can put CO2 is within deep, porous and permeable, saline, non-potable aquifers. And that's already been proven extensively, particularly in Norway, where in the North Sea, in the Sleipner field, Sleipner produces methane with a 30% or so CO2 content. The CO2 is stripped out before the methane is sent to shore and re-injected at a short distance away into a deep saline aquifer about 1 kilometer beneath the seabed. And that process has been going on since the mid-90s, about 1 million tons per year, small on a global scale, but significant in its own right. And that CO2 has been tracked in the subsurface on an annual basis. One of the other small-scale projects which is working now is within Iceland, where I think I mentioned before, CO2 produced in this particular instance, not from fossil fuel, but a small proportion of CO2 is produced from the deep hot geothermal industry. That's been re-injected into basalt. It reacts with the calcium and magnesium, the alkali earths within the basalt, to produce carbonate minerals. The same happens naturally in the mountains of Oman. They are ophiolites and mafic minerals forming the mountains, and they are reacting with percolating rainwater to take CO2 out of the system, out of the atmosphere. But of course, the rate is much slower than you can effect using CO2 injection into things like basalts. I mentioned on slide 2 or 3 that the UK became one of the top petroleum producers at the turn of the century. It's had an exploration and production business in the offshore since the early 1960s, and some 30 million barrels of oil equivalent, or a little bit more, have been produced. Around about 10,000 wells have been drilled in the North Sea and associated areas, and in the order of 400 fields have been developed. Of course, the 10,000 wells have not only been drilled on successful oil and gas accumulations, but also in unsuccessful areas. But nonetheless, it means that we now understand the North Sea as a piece of subsurface geology, as well as anywhere on the planet. I would say, having worked in the petroleum industry all around the globe, between the UK, the Netherlands, and Norway, this piece of real estate you see on the right-hand side is probably the best bit of offshore real estate that's known from a geological perspective, and probably comparable in terms of understanding the geology to things like the Western Canada Basin, Gulf of Mexico, and so on. And what we have here is now a 50-year-old industry, lots of offshore facilities, but very little petroleum coming out of the system now, systems which are nearing abandonment with all the financial liability that will bring with it. And in this particular instance, these facilities can form a huge CO2 storage opportunity, not just for the UK, but for others to export to it. On the left-hand side, it just shows the major CO2 producers in terms of where they are on the island of Great Britain. And on the right, the green areas are the oil fields, and red areas are the gas fields, and the blue outlines are some of the major deep saline aquifers which exist. And you can fairly easily envisage a similar trunk line system for delivery of CO2 into the subsurface that now exists for, or partially exists, it certainly was very large in the past for petroleum production. And let me just show you one particular piece of acreage on which I've worked in the past. This is in the southern North Sea, so offshore the east of England. You can see on the map on the left-hand side, there are a bunch of red discovered and producing gas fields. They tend to be quite deep. And shown in the middle of that is the endurance structure. The endurance structure is shown in cross-section with the seismic section. It's a dome-like structure formed over a salt swell. The main reservoir in this particular interval is at about 5,000 or 6,000 feet down and formed of medium-grained fluvial sandstones with a high net to gross and very good porosity and permeability for the most part. And this endurance structure is one that was drilled in 2013 by what was called National Grid Carbon in order to test it for suitability as a CO2 storage site. And it meets the criteria in terms of integrity of the trap rock, ease, high permeability, and therefore ease of injection. It was about to go through probably to the first trial when back in 2015, Her Majesty's government withdrew funding from the then CCS competition. I'm glad to say that Endurance, along with several other sites in both the North Sea and the East Irish Sea, which separates Wales from Ireland, are now actively being pre-developed, let's say, for CO2 storage. The UK government will make a decision towards the end of this year as to which sites will receive support to make those first important CO2 injections happen. And this endurance structure is large. Those the blocks which you can see on the left-hand chart are 12 kilometers east-west by about 18 kilometers north-south. And so potentially you've got several hundred million tons of CO2 which could go into this structure, and many which are similar to it. The internal characteristics, just to show you what it looks like, the satellite images are taken from an analog within the Tarim Basin in China. These are fluvial systems with active channels, braided, very high net to gross, maybe 90–95%. You can see the actual sandstone at outcrop, I should say, on the south coast of England, and that's shown in the little inset photograph. And you can see some of the modeling we did in terms of CO2 plume development shown in the inset modeling diagram, the colored red and blue. And because of the lineation of these systems, which is more or less exactly north-south, you would tend to see movement of the CO2 in both directions, but less movement across the way. And so, you know, it's not just the decarbonisation of the petroleum industry per se, but also making best use of the skills and knowledge base of those operating. In the UK at the moment, there's some 37,000 people directly involved with the petroleum industry, and another 250,000 in the support services. And whether it's CO2 going in or petroleum coming out, the sort of things that you will need are almost identical. So there's a great opportunity for making the most, not just of the pore space we have in the North Sea, but also the operations, drilling and completions. Adrienne, pipeline installation operation, as we mentioned before, injection now CO2, learnings from injection of water, measurement, monitoring and verification. And I think probably one of the most important things that we can learn from the petroleum industry is they know how to do big projects. And these surely will be enormous projects, the sort of things that would normally scare startup companies, big petroleum can operate. Of course, it would need to be predicated on a system of remuneration, which is associated with carbon taxation. Again, that's beyond the scope of this particular presentation, but that's something which needs further development. So we can look at scope 1 emissions now briefly. And I was working in South America in the early to mid 90s. And I returned to the UK, not having worked on petroleum there for some years before that, to find the beginnings of the downturn, not of the industry in terms of oil price, but rather in terms of the amount of accessible oil. I came back to a system in the mid 90s where fields were getting old. They had low and falling production of oil and gas, initially very high water production, and even that started to fall off, low gas production. And in this particular instance, I take the northern North Sea, so offshore the northern tip of Scotland, power depleted. Fields were failing here because typically gas would be produced with the oil, the gas burnt to give you power, the power used to put water in the ground, the water helped move the oil from the ground, so-called sweep. This was failing. There wasn't enough power, so not enough water was going in the ground, so even less oil was coming out of the ground and into the vicious circle that eventually led to the demise of quite a few fields, still having potential. So I'll take you through a story of just how important that can be and how we might be able to turn that around in some instances at least. So many of the fields in the North Sea are about 100 degrees centigrade, 3 kilometers or thereabouts. Some are hotter, some are a little bit cooler. As fields age, they tend to produce associated water. And in the case of the North Sea and this particular province, for every barrel of oil that was being produced, these fields were producing 10, 15 or 20 barrels of water, I should say, water at 100 degrees centigrade. So I first looked at this kind of opportunity in Colombia back in the late 90s. The Canyon Limon field in the middle of Magdalena Valley at the time was producing 1 million barrels of boiling water a day. That's around about 150,000 cubic meters of boiling fresh water in that particular instance. I asked my engineer what you could do with that water, and he said, in no uncertain terms, it's low grade, you can't do anything with it. And I had to keep asking that question. And eventually, Alison Old, who co-authored this paper with me, said, well, of course you can do something with it. The quantity of water is so important here that despite the grade of this energy being quite low, the volume of the water means you can work it. And this is just looking what you get out of a heat engine, an organic Rankine cycle. Fields like Ninian, Brent and Statfjord, which were producing around about 500,000 barrels of boiling water per day or slightly above boiling, could produce several tens of gigawatts of electrical energy. In fact, around about 50% of the power requirement. So you could get out of that vicious spiral. You could decarbonize your production, because you're not now burning gas or importing diesel and burning that, and so help the system there. Indeed, you can upgrade the water which is produced from the fields by taking things like the any other power generation and taking the heat, the waste heat from that system to further upgrade the water and again further reduce the emissions. So it doesn't take it to zero emissions, but it could substantially impact the emissions that are associated with production. And this didn't happen when I came back to the UK. I ended up setting up a couple of companies, one of which, rather, I should say, Fairfield Energy, ended up rather mistakenly, I would say, buying an old field called Dunlin from Shell. It had very little gas dissolved in the oil. The gas was used for power. Originally, power as electricity came from Brent, but that was getting old. And so power outages became the real production choke on what was happening in Dunlin. Immediately, the company started to transship diesel, a very negative thing to do, particularly in environmental terms, let alone emission of CO2. We could have exploited shallow gas adjacent to the field within 2 years. Looking for deep gas proved not to be viable. One of the things we could have done, and I couldn't get the chairman to agree to, was exploit that co-produced water. We could have had an organic Rankine cycle engine or two on the drill deck within a year. The company chose not to. It took build its own gas pipeline to buy very expensive gas to burn for power generation, and that took about 6 years. Once I'd left the company, I started to look at the impact that had on the bottom line. The field basically failed and was abandoned. So I looked at the decline rate for the field. This is a decline rate in red fitted to the actual production. And we know when that pipeline was installed. And so we can assume that access to power was not available once the pipeline was installed, and therefore prorate the downtime, which is represented effectively by the displacement of the blue from the red line, associated both with loss of power and other things. And of course, other things I can't do anything about. So other things are represented in blue, but the loss of production due to absence of available power is shown in red. And that becomes a very simple matter to look at the value of that integrated over the period of time, taking into account the oil price. So the loss in revenue to the company over that period of time was getting on for $750 million. So not only could you have produced a much cleaner, lower carbon system by exploiting the value of energy within the co-produced water, but you would have also improved the economics of the field quite dramatically, and it may still be producing today. So again, it's not going carbon negative or even carbon neutral, but it is beginning to reduce the total impact from the petroleum system. So now we've accumulated CO2 as a possibility for CO2 storage, and we've looked at the opportunity to ameliorate at least some of the emissions caused by using geothermal water. The scale of this co-produced water is substantial. We know what amount of oil is produced globally. Countries tend not to be very good at reporting their produced water for obvious reasons. So my estimates are somewhere between 7 and 38 billion tons of co-produced water per annum associated with those 4 billion tons of produced oil. Let's make a really gross assumption that it's about 100 degrees centigrade. Clearly some is a lot hotter, some is rather colder than that. But that gives you around about 800,000 to 4.5 million megawatts of power potential, which is being completely ignored. In fact, that amount of non-produced power from the petroleum industry's co-produced water is bigger than the global geothermal industry. This is not a small number, big numbers in this particular instance. So if we did power production from hot water, we'd reduce the need to burn oil or diesel or even gas for power generation and reduce emissions. It also happens to deliver colder water. And if you think about the North Sea at 4 or 5 degrees centigrade, very cold water for re-injection. That would improve the mobility ratio relative to the oil, could induce thermal fractures, which would further reduce power requirements, and extends field life and helps maximize economic recovery whilst reducing total emissions. Over the last couple of years in the UK, I'm running a bit slow here. I'll speed up a wee bit, just a couple of slides to go. People have started to use the word, or use, carbon capture, use and storage. And for a long time, I began to think that the U might indeed stand for unicorn, given this energy diagram on the right-hand side. But there are a couple of things I think might work very nicely, and these are in the early stages of investigation. There are a lot of stranded assets in the North Sea, small gas fields, unproduced. Might we, instead of ignoring those, produce the gas on site, burn it to produce power, plug the power into the new and existing wind farm network to reduce intermittency, capture the CO2 and re-inject the CO2 underground? Technically, all those things work. Putting them together would indeed bring some challenges, but it could be made to work. So the UK could improve its energy security perspective at the same time as reducing the need to bring gas on shore and capture the CO2 and re-inject it. Another twist on that is thinking about what happens to CO2 in the subsurface. Now, I mentioned that those fields up in the northern North Sea could produce about half the power requirement if they use co-produced water. Part of the problem with using co-produced water is it needs to be re-injected in the ground. And that takes an awful lot of energy. And that's why they're not net energy producers with water at 100 degrees centigrade. But if instead our power fluid was CO2 rather than water, because it's got a much lower viscosity and because its density is pressure dependent and temperature dependent, you can set up a thermosiphon. So CO2 storage sites, possibly those generated from the gas to wire concept, could quite reasonably become geothermal power stations with the dense phase CO2 circulating from the deep subsurface to surface, driving a turbine and producing power. The cooling of that CO2, still within a closed system, takes it back into the ground. This CO2 plume geothermal, and we're working this with Martin Zara at ETH Zurich and others in Potsdam in Germany, has taken us to the point where with colleagues within the industry, we've created a new not-for-profit company, Shift Geothermal, standing for Sustainable Heat In-Field Technology. The aim here is to advocate and create the framework whereby at least part of the North Sea industry could move from being the major producer of carbon to one in which it might be carbon neutral or even carbon negative if CO2 is captured and used from biofuels. There are other things we can do, and just very, very briefly to finish off. A number of years ago, I tripped over the possibility of producing helium from a field in South Asia, which had been completely overlooked by the company that owned it. And that set me on a path of trying to understand why no one had really ever tried to explore for helium, a critical element for the energy transition, and one which is also used extensively within medical cryogenics. Cut a long story short, we developed a strategy and went on to find helium without associated hydrocarbons in Tanzania. And we're now turning our attention to the possibility of finding native hydrogen. Some of you will be aware that an accidental discovery of native hydrogen in Mali is now on production and producing 95% pure, natural, as I would call, gold hydrogen. So there are a series of opportunities that we can think about in terms of scope 1 and scope 3 emissions associated with CO2 injection, CO2 or brine geothermal, gas to wire, and so on and so forth. So a whole range of ways in which we could begin to start to transform the petroleum industry and decarbonise it at the same time. Thank you very much indeed.
Thank you very much, Jon, for the talk. Thank you for this great overview of the path to decarbonization. So we're now open to questions. So just feel free to unmute yourself and ask your question.
Hi, Jon. I'm Laurent. Thank you so much for giving a talk to our audience. I'm the labs director, and I wanted to hear your thoughts on brine production, co-produced water that you had mentioned. Could there be interesting things chemically in that water to make it commercially even more viable? And of course, we're all talking about lithium here.
Have you been reading my papers? Yeah, I think there might be. Clearly, there may be issues. First of all, you re-inject the water, and you would re-inject it once you've taken the heat out. But you're very right to say we need to examine those waters for possible economic components. The one in terms of solutes which interests me most is lithium, and we know, for example, well, I work on a helium. I work on a geothermal province very close to where I live in the northern England, which we drilled into a granite, and that has big fissures within it, water which we know is equilibrated at 100, 150 degrees centigrade, and it's 100 ppm or above lithium. We don't know the volume of the water yet, but a company, not by me, unfortunately, has now been founded to try and exploit that lithium. So lithium associated with granites, possibly also associated with areas of evaporite. So again, in the southern North Sea, the main cat rock is salt, as in halite, and I don't think anyone's looked significantly properly as whether or not some of those systems are rich in lithium. One would expect them to be so. Another field in the North Sea is reported to be pretty much a mineral deposit, and so things like a dissolved zinc within the formation waters are also of interest, although I think the field has essentially ceased production now before anybody took that seriously. In terms of in a global sense, the Smackover, which is a Jurassic limestone in the lower 48 of the USA, that has been exploited in one area for its lithium content, and quite frequently co-produced water from the Smackover is in excess of 100 ppm lithium. So yes, it behoves us to look at all of the dissolved components. I'm speaking now with an American audience, but I tend to think of the opportunity as being similar to what the Dutch called total football in the 1970s. Every player could play in every position. Although they never did win the World Cup, beaten by Germany and Argentina on two successive occasions. But the opportunity, I think, as part of a circular economy, we need to understand all of the components, the ones we don't want, the ones we do want, and over and above lithium, I'm sure there are some species which would, in some instances, prove valuable co-products to co-produce water and petroleum. Yeah.
Thank you. I see Amy has a question.
Hi, I'm a research scientist in ERL, and I have a sponsor for from a national oil company, and we were talking the other day, and he says his company does a fair bit of carbon sequestration and offshore wind, but more than 95% of their bottom line still comes from selling oil and gas, and that's kind of an obstacle to, even if everything you're describing, which are such interesting possibilities. How do we add the economic side to make it something that a company wants to do profitably? And I'm thinking of, how do you measure profit, and how do you measure cost, and what's not being accounted for?
Yeah,
But there needs to be a change so that they really want to do it. I mean, you can force them to do it. That's hard and possible, but it's hard. But it'd be nice if it was really economically profitable.
precisely. And that comes back to that energy chart. The problem at the moment is that we get an awful lot of energy out of a very small volume of fluid, and it's easy to transport, it's easy to keep. But what we don't do is account for, I know millions of people are in energy poverty, but if you go back 2 or 3 generations to our grandparents, great-grandparents, they would have spent an awful lot of their time gathering energy, likely firewood. We've got hooked on a very cheap energy source, in part because we haven't accounted for the cost of tidying up. In fact, I only know of one industry that recognized it had to tidy up before it started operations. And you can argue how well it's done or not, and that's the nuclear industry. It factored into, maybe not well enough, but certainly partially factored into the nuclear industry is the cost for dealing with the waste. And sooner or later, we're going to have to come to that, however we measure it. I'm not an economist, and I struggle with some of the economic concepts, but bear with me just for a moment. About 20 years ago, the UK started to promote offshore wind. It was very expensive indeed. But we're on, generation 4 or 5 now. It's now competitive with petroleum. That's been achieved over that 20-year period. Similarly, clearly there are other environmental impacts here which I wouldn't shy away from. But similarly, the current generation and manufacturing might of China when it comes to photovoltaics now mean that photovoltaic panels are within in the West very competitive with other energy vectors, and so we're ingenious as a species. But ask an economist how we work this through. I think at the outset, though, we've got to do it through either direct or indirect taxation. We need to pay for the tidy up. If we don't recognize that, we're stuffed, basically.
Thank you. I think that's true. I think there needs to be a price on doing it wrong.
Thanks. Any other question? Maybe I can slip my question. We discussed already before the use of CO2 for geothermal. If we had to write down a table and compare water and CO2 in terms of advantages and disadvantages, what could we say for both fluids? You mentioned the viscosity, the lower viscosity of CO2 and the ease to put it back in.
So overall, the calculations, Martin Saar at ETH Zurich and a guy who I think I might be back at MIT now, I'm not sure, I need to check, called Ben Adams, would suggest that the net power output of a CO2 system under conditions of around about 100 degrees centigrade, and I forget the suggested required permeability of the rock, is about double that of water. So water has a much higher thermal capacity than dense phase CO2, but it requires this parasitic load to put it back in the ground. So with CO2, you get a net net energy, or in terms of power, electricity production, which you struggle to do with water. With higher temperature water, of course you do, because that's how what you might call traditional geothermal systems work, with superheated water or wet steam, which is then flashed. So that's really the comparison. What we don't have at the moment is a demonstration scale process using CO2 plume geothermal. We, along with Potsdam and ETH Zurich, Shell, Siemens, MAN diesels, and a couple of others, put in an unsuccessful bid last December. So we'll keep trying. You know, a large scale bid, which would have that was with. Was it with Aquistor? Yes, it was with Aquistor in Canada as well, who of course have been putting CO2 in the ground since around about 2015. So if anyone's got 20 million, we can have a go.
Thank you very much.
Yeah.
Who did you say at MIT? Ben, did you say Ben Adams?
Yeah, he's certainly come back to the States, Ben Adams. He came back just quite recently. I'm not quite sure where he is. I'll check it out.
Thanks.
So, any other question? We might thank our speaker again. Thank you very much, Jon, for the discussion and for the presentation. Yeah.